Hi, I'm Scott Jacobian. In this video, we're going to look at velocity and force transformations. So by the end of this video, you should be able to implement velocity and force transformations. So we previously saw how we can find the Jacobian for our robot manipulators. We had two approaches. We could use joint directions and derivatives, and this was the formulation. As well, we could use joint directions and cross products, and this was the formulation. Now, when we did this, we could choose a point on our end effector, and then we had a reference frame. Now, that point that we used to calculate, so in the case of joint directions and derivatives, we used the point from the origin of the base frame to the origin of the end effector, or for the cross product method, we used the point from the origin of frame I to the origin end effector. It could be any point on our end effector. Now, some points make derivations and computational complexity simpler and more efficient. So if we choose this point appropriately on our end effector, we can actually make the calculation of our Jacobian simpler. Now, let's look at an example of that. Suppose we take a point attached to our end effector and make it coincident with the center of our spherical wrist. All right, so it's a point on the end effector, but it's located at our wrist center. So our Jacobian of our end effector is equivalent to the Jacobian of the wrist. All right, and if you were to work out that Jacobian, you would get a Jacobian of this form, where you have this matrix of 3 by 3 matrix here of zeros. So this would make calculation of your Jacobian a lot simpler, because you have a 3 by 3 matrix of zeros here. And things like calculation of our singular configurations, which we're going to talk more about in a subsequent video. But if we wanted to calculate the singular configurations, we need to take the determinant of this matrix. So if we were to take the determinant of JW, well, because of that formulation, it would just simply be the determinant of A times the determinant of C. All right, so that would make calculating the singular configurations easier. Our velocity would be of the wrist center now, times our Jacobian, times our vector of joint rates Q dot. Where VW is our translational velocity of our wrist and our angular velocity of our wrist. So we can make a note. VW is the translational velocity at a point coincident with the wrist center. Okay, so now we could use this formulation. Now, often we have the velocity of our end effector at, say, the tooltip that we want to move it at. So we need a way to actually convert our velocity at the tooltip to be the velocity at, say, the wrist center. All right, and to do this, we need a velocity transformation. So suppose we have points A and B, and two respective reference frames with orientation C and D. So suppose we have a rigid body here, and we have frame C over here, and suppose we have frame D over here. We have 2 points. We have point B, and we have point A. And our rigid body has angular velocity omega, and say velocity A here. And suppose we know this vector r b to a. So let's write what's known is the velocity of a with respect to frame c, which is the translational velocity, and the angular velocity. And what we're trying to find is the velocity at point B with respect to frame D. So that's the translational velocity of point B and the angular velocity with respect to frame D. All right. So our angular velocity, let's deal with that first because it's simpler. The angular velocity of D is just simply going to be the rotation matrix describing frame C with respect to frame D's orientation times omega C. Okay. Now the velocity, the translational velocity of B with respect to D, it's going to be the velocity of A with respect to C plus the angular velocity omega with respect to C cross our position vector r a to b with respect to C. And then this all has to be multiplied by r c with respect to D. So we can write this out. Okay, and now this cross product, okay, we can actually multiply in by the r, and then we can flip the direction of the cross product, so we can change the direction of this vector. All right, and so if we do that, we're going to have D, frame D, B to A, that's r, cross dcr, our angular velocity. All right, and so that's the translational component. So we can then write this as a matrix equation where we now have a velocity transform. So T subscript V will be our velocity transform, A to B, with respect to C to D. So in essence, all we're doing is putting these two equations into a matrix form here. And now, obviously, we have to know what this T is. So that's our velocity transform. And it has this form here. And then in the upper corner here, we have R tilde, which is a skew symmetric matrix that allows us to do that cross product. So I'm just going to write that over here. R tilde B to A is just simply the skew symmetric matrix of this form. All right, with RB to A, just simply RX, RY, and RZ. All right, so this is a skew symmetric matrix that allows us to do the cross product. All right, and so this is a 6x6 matrix that converts our velocity from one point to another point and from one frame of reference to another frame of reference. All right. Similarly, we can do a force transformation. And so for the force transform, what would be known is our wrench at point A with respect to frame C. So it's our force and our moment. And what we're trying to find is our force at our wrench at point B with respect to frame D. So our wrench at B with respect to frame D is going to be a force transformation now. So we use a subscript F for force transformation. C to D. A to B here. All right, where the force transformation has a similar form as the velocity transform, but it's a little different. Our skew symmetric matrix is in this corner now, just by the way we defined our wrench. All right, and again, this is a 6x6 matrix. So don't get confused with the force transformation and the velocity transformation with the T we use for our homogeneous transforms. All right, so this will convert the force, our wrench here. That's A. This should be lowercase a, sorry. A at point A with respect to frame C to point B with respect to frame D. All right, and similar, we had our velocity transformation. All right, and so with that, we can then use our Jacobian with respect to any point on our end effector.